Before we begin the lectures, just a small few announcements. So we found a lot of messages yesterday and day before that a lot of you have not received the invite for PB Works, but subsequently many also had informed that the message was found in your spam folder, and you have then been able to access a PB Works page for the summer school. So if you still have not received the PB Works invite, please do write again to the ISSAA@iucaa.in. And before that, please do a thorough search in your spam folder to see if the invite from PB Works has been flagged as spam or junk and is lying there. It is most likely there because we have sent the invites to all the registered participants, and you should be able to access them. But in case you are not, then write to us again. We will send another invite. Well, I have been informed that more than 90% of the participants now have been able to access PB Works, and it's only a small fraction who have not. But still, again, before you send us an email again, check your spam. So on the PB Works website, you'll find that we will keep updating the schedule of the lectures. If there are any minor changes in the schedule, we'll update that there as well. And I can understand, since there are a large number of participants this year, it is very difficult to conduct the Q&A in the limited time. So we have been trying to devise better ways to address this. One way that we will try to test from this week onwards is, for each lecture, we will upload a link for a Google form. So for that link, you will have to mention your name, your email ID, and your educational institution, and the question that you have. So this the link to the Google form will be available in the PB Works website. Please do not share the link outside of the summer school participants or the refresher course participants. Please do not share it with your friends. If we find that you have done it, we will strongly request you not to do it and caution you, because we will sort of get overwhelmed if we start receiving too many questions outside the participants, and this is already quite a large number of people. So if you have any questions after the lectures that you are not able to ask, either due to lack of time or something that came to your mind after you have thought about what was taught, you can go there. We will type in your query. We will forward these to the instructors, and if the instructors have the time and to address those questions, they will. Okay, so please check the PB Works website later in the day. So our technical help is just working on this now, and then you do it. Okay, so now I will start the lecture. But again, before I start, let me stop the share and see if anybody has any questions. So if you have any questions right now, please raise your hands and we will try to see and resolve some of the issues. Yes, who is this person 578144? And before I ask you to unmute yourselves, whenever you join in, please join in with your proper name, your name and surname, so that we know who we are talking to. Do not use names such as a jumbled letter of words, which I just saw right now, FSGS, whatever that is, or numbers like this, 57188144. If we do find such people, we will remove you from the Zoom link. So I'm unmuting you, 578144. Please identify yourself and ask your question.
Hello, sir.
Yes.
Shubham Sahu here, sir.
Yes, Shubham. You should rename yourself. Otherwise, Shubham, we will.
Okay, sir. This is, sir. Actually, what is the problem? Last class I was unable to attend because due to some exam.
Yes.
So how can I attend that class, or can I get the recording?
The recordings will be available on YouTube in the IUCAA link.
Okay, so today lecture, sir, is there any problem for me to understand, or
that you'll have to figure out, Shubham? We can't help you with that. Okay, next question, please. Guru Prasad. Yes, Guru Prasad, please ask your question.
Yes, sir. Good morning, sir.
Yes.
Sir, actually, yesterday I have not received about the PB Works website link.
Yes, Guru Prasad and others, if you still have not received the PB Works page, as I just said, check your spam folder, and then if you still have not received the PB Works invite in your spam folder, then write to ISSAA@iucaa.in. Okay.
No, sir. Yesterday I wrote to the
Yes,
mail ID.
if you have written Guru Prasad, then somebody will respond to it and add you there. Okay.
Yeah, sir. Yes, sir.
Okay, so for the others who have raised your hand, if you have questions other than PB Works, then only you can keep your raised hands. Otherwise, lower your hand. Unique.
Hello,
Yes.
sir. Good morning.
Yes.
Sir, actually, I had a question regarding yesterday's lecture, the last portion of the lecture. Sir, on the last part of the lecture, where you explained the transfer equation, that is the general initial transfer equation.
Jinek, your audio is extremely poor. I can't really hear the question. So what I would suggest is you withhold your question for now, and when we create and upload the Google form, you write there. I will try to address it there. Okay.
Okay. Thank you.
Okay. Yuvraj, I'm asking to unmute yourself.
Am I audible, sir?
Yes.
So I have a general question. So
yes.
If we have IR radiations not entering the Earth, which means the components of the atmosphere observes and re-emits back into the space.
Yes.
So if that is the case, while looking for exoplanets and other planetary systems, should we look in IR regions to find such planets which are rich in water vapor or other organic compounds and all?
Yeah. So these are the techniques that are actually used when you should look at some of the results from the Keck telescope, and also from the Subaru telescope, and they have excellent spectrographs for detecting exoplanets there, and they use this sort of techniques to understand the emission or the re-radiated emission from the exoplanets. Of course, as you rightly said, even Earth has a strong signature in the IR, especially in the night side of this region. And IR and other sort of emission lines are also used to understand the atmosphere. So I am not an expert on exoplanets, so I cannot give you further information on this except the general information that I gave. But you should look up the more specialized websites that are there for the instruments on Keck and Subaru, who actually do try to detect exoplanets from direct detection. And this is a big thing now because I think somebody will talk about adaptive optics. But if not, then due to atmospheric turbulence, it becomes very difficult for us to observe things outside and things get blurred. But we have now developed specialized several decades now, devised specialized techniques to actually reduce the effect of atmospheric turbulence. So the same reason why stars twinkle. And with this, we can actually directly detect exoplanets now, Jupiter-sized exoplanets. And these are try to detect in the IR bands, but the IR is heavily absorbed. So that is why one of the major quests now is to go to space telescopes and detect these exoplanets using space telescopes. So you should also look up, for example, if you're interested in exoplanets, look at the TESS, and the other Kepler telescope. I'm not sure what the wavelength for Kepler is, but TESS is, and also WFIRST. All these space telescopes, and even JWST. All these space telescopes, JWST is IR, and all these have strong science cases for detection of exoplanets. So I'll refer you to those. Thank you, Raj, for your question. Jyotirmoy, unmute yourself, please.
Yes, sir. Good morning, sir. Most of the cases, it is seen that absorption spectra are broader than the emission spectra. Why it is?
I don't know if that is the case, Jyotirmoy, that most of the cases have absorption broader than emission. It depends on the properties of the system that is absorbing or emitting the spectrum. I know absorption spectra of systems that are quite narrow, but emission spectra are quite broad. So in astrophysical systems, it depends totally on the internal properties of the substance that is affecting your spectrum. So if your emitting region has a lot of turbulence or a range in velocities, then the spectra will be quite broad. On the other hand, if your absorption spectra is coming from a small region of cloud, which have very correlated velocities, and there is not a much a spread in the velocity, your spectra will be narrow. So this is not the case, and it depends totally on the properties of the system. Thank you, Jyotima. Maybe the last question, Priya, and yes, Priya.
Hello.
Yes.
Good morning, sir. There's a general question rather from the talk today right now. It is that yesterday, the third lecture in the afternoon, it had a lot of turbulence with the connection from sir's end, because of which the lecture was completely unclear. So what can we do in such a case? It's difficult. It was difficult to follow.
You cannot do anything about this, Priya. Unfortunately, the situation we are facing right now because of the pandemic, we cannot have a live lecture. So in case of technical difficulties like this, we'll have to live with it. Okay. If the instructor can manage to have a better connection, then everything is fine. But there is nothing more that we can do from our side for that. Sorry.
Okay, I was thinking if we could have slides or something to follow up for that.
Yes, the slides will be uploaded as Dipanjan said, but at the end of his lectures, because he's still preparing the slides and changing them. The slides will be available. You can also go back and check the YouTube link because the YouTube recording is there. And maybe once you review the recordings on YouTube and the video, it will become a bit more clear for you.
Thank you so much, sir.
Okay. So unfortunately, I think I will have to start the lecture for today. Otherwise, it's getting late. So as I said, we will try to create a platform for you to submit further questions, and then we'll forward them to the instructors as and when they get prepared. One last announcement for today. Shomak's lecture in the later half of in the morning from 11:30 has been shifted to the afternoon. So Shomak's lecture will take place in the afternoon at 2:30. Sorry about that. And Dipanjan's lecture has been shifted forward at 11:30. So this is just an announcement. Okay, so I will share my screen now. Okay, so welcome everyone once again to the second lecture of the radiative processes. So in this lecture, so the first two lectures and even maybe the third lecture, we are sort of trying to build the basis of the formalisms for radiative processes. And in the middle of third lecture and fourth lecture onwards, we'll go into the introducing to you some of the basic processes that gives out the radiation. Because this is just a 4-lecture series, and this thing that I'm teaching right now, this is almost a half a semester course that I teach. And so it is very difficult to condense everything. But I hope the lectures is not supposed to be comprehensive, but gives you a flavor of what is involved here. And that can motivate you to learn more about these things as you feel more interested. So yesterday, we learned about some of the basic definitions that we use for radiative transfer. For example, the definition of the intensity flux. How is the intensity related to the energy density, etc. So we'll carry forward from there. And then we will try to see, as we are moving along an array, how will the intensity change if it encounters a different material that are emitting emission, also different material that are absorbing the emission. So for example, let's say you have in a region of space some matter that is emitting energy. Okay, and let's say what we define in this case to characterize the emission is something called the emission coefficient, J nu, small j nu, which is, the definition is the energy emitted per unit solid angle, per unit time, per unit volume, and per unit frequency, essentially. So the total energy, since these are all the quantities that are divided, so the total energy that is emitted in the unit in a small volume delta V is J nu times d omega because it's per unit solid angle, then dt because it's per unit time, and d nu because it's within the small frequency range, and delta V. So you take a small region of space with the volume dV. And in time dt, this is the amount of energy that is emitted into a solid angle. Why a solid angle? Because what we are trying to understand is a ray that is passing along a direction. So what we are trying to see is along the direction of that ray, that you can define a solid angle and what is the amount of energy being emitted in that direction. Usually emission like this can often be isotropic. So if it's isotropic, you will have to find the equal amount of emission is being given out in all directions. And that is why we are trying to focus on the fact that we're trying to find what is the emission in a given solid angle. And say, suppose, as I said right now, if the emission is isotropic with the power P nu because it's frequency dependent, power is energy per unit time per unit volume. So this coefficient J nu is just 1 by 4 pi P nu because we have to, the total solid angle is 4 pi steradians. So J nu per unit solid angle is P nu by 4 pi. The reason why I say this is because in many of the radiative processes mechanisms, what we actually end up computing is this power P nu itself. So once you know the process and get its power, you can find what the emission coefficient is. Now, let us then try to relate this to the quantity of intensity, as we have said. Because why intensity? Why deal with intensities? Because when we do radiative transfer, it is much easier to consider the radiation along a given ray. So that when you say, if you have an observer plane over here, and you can shoot different lines of sight or different rays from the plane of the observer. The observer can be the detector of a telescope. And these rays will pass through different locations in space and sample different regions. And that is why it is much easier to consider the variation of emission along different rays. And that is why we talk about things in terms of intensity. So what we want to find out is, as a ray passes through this region of volume that is emitting, how much of added intensity is added to that ray. So the ray, as it is progressing, it has a specific intensity I nu. And as it enters the region and then leaves that region, what is the new intensity that is added to the ray? So we just computed the total energy that is emitted in a given solid angle. This is delta E. Now, from the definition, just from purely the definition of intensity, intensity is the energy per unit solid angle, per unit time, per unit area, per unit frequency. So you can clearly see that you can immediately compare this. This is from the definition of intensity itself, or the small change of intensity as it's passing that region. And dE is just being substituted from here. And you can immediately make the connection. So note the main thing that comes here is the fact that there is a volume involved in the definition of dE, because the energy or the emitting process is defined in terms of the energy emitted per unit volume. So suppose you have that region of space has an area dA, and then the intensity or the ray progresses a small length ds or delta s over here through that region. So the total volume that you are now considering is this dA times ds. So it is all the same quantities here, but the delta volume has been replaced by dA times ds. Now you can see that intensity is in the energy per unit area. So the dA cancels off. And what you're left at the end is the small change in intensity is this emission coefficient J nu times this added length that the ray has passed. So the addition to the intensity is J nu times this small change in length. Just a disclaimer here that emission may be isotropic in the rest frame, but if you have, for example, the emission is being done by a system that is moving at with respect to you, and if the motion of that system is relativistic, then the emission pattern will become anisotropic. And this, I will try to see if I get into this today, or otherwise I'll talk about this tomorrow. So this is how you define the added change in intensity due to emission. Now what about absorption? So suppose your ray again encounters a material, and the material is filled with particles, electrons, molecules, etc., which can absorb that radiation. So make matters short, this is how it works. But let us try to see how this equation appears. Now, when you talk about absorption, or this is also applicable for scattering, but scattering becomes a bit more complicated because it becomes an integral differential equation. So I will not talk about scattering right now, but I'll just talk about pure absorption. So energy comes and hits a system, and the energy is completely absorbed by that material. And you can think of it in terms of, say, if you have a hydrogen atom that has electrons in the lower excited states, in the lower states. Now, the energy of the photon can come and interact with this atom and then excite this to higher energy states where all of that incoming photon is completely absorbed. Okay, so this is, and this interaction, as you would know from your quantum, from your lectures in quantum mechanics, usually have a cross-section area. So for each of this absorbing material or particles, we can always define a cross-section area over which the interaction will take place. So suppose there are n number of absorbers in a volume, which is dA times ds. So this is the ray that is passing through this volume, and this is the cross-section area, and this is the length of the ray ds. So dA times ds, this is the total volume that this ray sort of sweeps in time dt as it passes through this region. So let us try to understand what is the change of intensity as the ray passes and interacts with all these particles in this volume element. So of course, simply from the definition of intensity, again, we find that this should be minus di nu, because we have a reduction in intensity, times the area times solid angle times time times frequency. Again, this is just from the definition. Now, here is where the physics comes in. What we are trying to see, again, this would be elementary for many of you who have learned it in your lectures maybe, but these are important concepts to be sort of clear about. So then what we can find is, what we want to find is the total number of, the total volume that is being swept up. So what we have here is the n is the number density of the particles. So how many particles will this ray encounter? So if n is the number density, how many particles will there be here with, and what is the volume of the absorbing region? So volume, we first of all have a length, which the ray traverses. And then we also have an area, which is a cross-section area. So the volume that is traversed and that is actually doing the absorption, it is not dA times ds, but it is sigma nu, which is the cross-section area, times ds. And this multiplied by n, which is the number of scattering points, will give you the total volume that is actually doing the absorption. And this multiplied by I nu will give you the reduction in the intensity that happens as the ray is passing through this region. So cross-matching terms here, you end up with this fact that di nu is minus n sigma nu I nu ds. But n sigma nu is called the alpha nu, or the absorption coefficient. Now, this is something that is often referred to. That's why I've written it here. But the alpha nu is also referred to in terms of the mass absorption coefficient, kappa nu, but which is the absorption coefficient per unit mass. But these are just definitions. So different textbooks, different material use different definitions of the cross-section area as well as the alpha nu. And that is why it is important to understand this. But the fundamental point of these two slides is you now have a differential equation to understand the evolution of the intensity as it is progressing along a line. So for a small excursion along this ray, you can have an intensity added to that ray given by this J nu. So if I go back to the previous slide, sorry. So di nu is J nu ds. So di nu ds is J nu. And here again, di nu is minus alpha nu I nu ds. So di nu ds is minus alpha nu I nu. So collecting these two terms together, as you move along this path length, you can have an addition to your intensity as well as a reduction in intensity. And this is called the radiative transfer equation for the intensity. And this is the most fundamental equation that is widely used in all sorts of fields while understanding what is the emission that your telescope is seeing. So for example, let's say you have emission coming from a distant black hole or a quasar. Quasar are a different name for calling active black holes, which are strongly accreting matter, and that's why they're heating up. So this radiation is then passing from this distant object and coming towards you. But while it is coming towards you, it is passing through different material as well. The more radiation can be added to that ray as it is traversing different regions with different density distributions, or a part of the radiation can be taken away from this ray because it's getting absorbed by different regions. And this is how you actually solve these things. Yes, Ishwaran, I have noticed your raised hands. I will come back to you shortly. Keep your raised hands and keep your questions ready. So this is the basic definition of the radiative transfer equation. This is a more advanced definition of the radiative transfer equation. I will not talk about the derivation here, but if you are interested, I would refer you to the book by Mihalas and Radiation Hydrodynamics. What you see here is a full time-dependent radiative transfer equation. So what I talked about earlier is when the intensity of light has reached a steady state. But suppose along this ray, things are moving. So once the intensity goes to a different region, the properties of that region is changing with time. And if the rate of change of time is not not slow enough, then that will also affect the amount of intensity you're seeing, and that will change with time. So if your intensity or if your flux is not constant with time, we have to solve this partial differential equation. So the earlier was an ordinary differential equation. This is a partial differential equation. And what you have here is now this derivative of intensity along a path length, along the ray itself. But suppose you want to define it better in terms of a standard coordinate system. So the ray can be in any directions, right? And you have to take the derivatives along that ray, along that direction. But if you want to solve this now in a Cartesian system, then you have to define this derivative with respect to a standard coordinate system. For example, in the Cartesian system, you can change this partial derivatives using the chain rule, and this del x del s, or the change in x along that path length, all of these. So these are very trivial trigonometric relations I'm not going to define, and these are called the direction coefficients, nx, ny, and nz. So what you will end up with is this time-dependent radiative transfer equation can be recast as a vector equation, where you take the dot product of the direction coefficient with the divergence, and then act this operator on the intensity field. So in actual radiation hydrodynamic solutions, or when we do simulations of radiation hydrodynamics, we actually solve this equation. For any point in our system, we define the emission coefficient, we have the absorption coefficient, and we have, similar to fluids, you'll learn more about fluid dynamics, but the radiation field can be also considered as a fluid distribution, where every point in space, we have some definition of the INU. And this is how you then solve the evolution of INU at different points in space. Again, this is just an advanced thing, and you do not have to understand too much, but it's good to know that this is the final form of the equation that you have. Okay, so Ishwar had a hand raised. How do I? Participants, yes. So, okay, I don't see the hand, raised hand. Okay, Ishika had a raised hand. Yeah, did you have any questions immediately for this, Ishika?
Yes, sir.
Yes.
So, nx, ny, nz are the direction cosines of the ray.
Yes, that's right.
What does it actually means?
What does it actually mean? That this is sort of going beyond this. So you have to know what are the So let me unmute you again. Have you learned about direction cosines, Ishika,
yes, sir.
in your lectures?
So, my question is that is it only in the solvable way, or is it in it's a different thing or the same thing that
it's the same. It's the same direction cosines that you use for your standard trigonometric usage. Okay. Okay. Thank you, Ashika. Oh, maybe one last question on this part. Jay Kaushik, please unmute yourself.
Good morning, sir.
Good morning.
Sir, I just want to ask that here we study about the radiation coming from, suppose we are talking about black holes toward us through a medium.
Yes.
Sir, if we consider medium to be a fluid, for an example, and the fluid having properties that changes, it may be shear, it may be deformed, and it may even rotate. So how we can use these properties to understand and how they can change equations?
So the basic fundamental equation remains the same, that you have to solve for the radiative transfer equation. And if possible, you have to solve this time-dependent radiative transfer equation. Because as you rightly said, what we actually end up observing are time variable emission. And time variability in the emission gives us strong indications of what the system is doing. And I don't know if in the AGN lectures you'll be taught, but for example, let's say something is varying in the AGN or somewhere in space. And if you just know the delta t over which this phenomena is taking place, you can immediately place some constraints on the length scale, because the maximum delta t could be, or the maximum speed of variation could be the speed of light. So the length scale would just be c times delta t. So all these things are actually used. So for example, in jets from supermassive black holes or blazars, we can see a wide time range of variations of the intensity. And as you rightly said, as it is passing through different regions, they can add their emission at different times and add to the time variability. And in such cases, we do have to account for the time variable solution of the transfer equation. And it is not easy. It is complex. So we make approximations for that.
Thank you, sir.
Okay. So I will stop the questions here and resume the lectures, but keep your raised hands or keep your questions ready when I again pause and take the questions again. Okay, so now let us see some of the solutions of this radiative transfer equation. So forgetting the very complex things that I was talking about right now, the fundamental thing that you have to remember is this. And this will actually take you forward and finding out the radiation intensity in most of the cases. So some applications, for example, consider that there is no emission. You have a uniform intensity that is coming and entering a region and is just getting absorbed. Okay, for example, one of this is, for example, the radiation from the sun that is coming and entering the atmosphere, and it is getting absorbed in the atmosphere. So there, if you know the alpha nu of the material, you can immediately solve this. This is an exponential solution, and you can find that the radiation will decay exponentially depending on the path length of the radiation, or the range over which this radiation has crossed the material. And you can see that within the exponential, this is a very trivial solution. You have this integral of this alpha nu coefficient along the path length. Now, this integral is very important, and this is something that we call the optical depth. And the full optical depth is just the integral of the alpha nu over the path length over which the ray is passing through it. But you can also write it in this differential form, which is d tau nu equals to alpha nu ds. And when you, if you can find the optical depth, then you can recast this solution as just the I nu at a certain point as inside the medium is equals to the intensity outside the medium, or at the starting point of the medium, which is S naught, which is the starting point going to S. And this exponential minus tau nu. Now, from here itself, we can make very important conclusions. For example, if the medium is very small, so the absorption is not that effective, then in that case, if tau nu is less than 1, you can sort of ignore this. And such cases are called optically thin medium, but the absorption does not really affect the intensity too much, and so we neglect any effect of absorption. However, if your tau nu is greater than 1, then your intensity starts to significantly decay because of this negative coefficient in the exponential function. So your intensity starts getting attenuated, and this is called an optically thick medium. So just by considering this integral, you can immediately define or understand the property of the material, whether it is going to absorb the intensity or whether it's going to decrease, not affect the intensity, without formally solving the radiative transfer equation. Now, this was a simple solution where you do not have the JNU, but if you do end up having the JNU, the solution is not so simple like this. But even in those cases, just by considering the optical depth, you can get an idea that the intensity, whether if the incoming intensity will be absorbed or whether we can sort of neglect the absorption part. So this is a very fundamental thing, again, that we do, that we often do back and envelope calculations when we try to understand what will happen. And in astronomy, many, in most of the cases, we start off with extremely, let's say, approximated calculations with a lot of spherical curves. And this back of the envelope calculations gives us order of magnitude estimates that then help us in improvising and making our analysis more sophisticated. So this is how you define optical depth. Now then, even from this basic definition itself, you can get another important quantity, which is the mean free path. Now suppose what one can then define in some way is what is the probability of a photon to get absorbed. So suppose a bunch of photons are coming and entering a medium, a fraction of them will get absorbed. And the fraction that will be absorbed is exactly given by this equation. So if you turn it back in a probabilistic sense, you can say that the probability of getting absorbed is exponential minus tau nu, which is just the solution that I had here. So the mean optical depth, as you are, optical depth can vary from 0 to infinity. So mean of optical depth will look something like this. You have this optical depth tau nu, and you multiply by the probability and integrate over the entire range. And the mean optical depth will be 1, because you can get completely absorbed. And then what you can do is, as you know, the optical depth definition is just the integral of the absorption coefficient over the path length. You can find the mean region over which the absorption is taking place. So you can approximate this integral and replace it, with alpha nu, L nu. So this gives you, again, so we're talking about mean quantities here in a probabilistic sense. So just by following this chain of arguments, you can see that for an optical depth of 1, that is, object is getting absorbed, you can define a mean length over which this phenomena will take place. So the mean free path now is, since average is 1, because we want it to be absorbed, you have the mean free path is 1 by alpha nu, or 1 by n times sigma. Again, from your basic kinetic theory of gases in your lectures in bachelor's, you must have arrived at this in a slightly different way, but you can also think of it in terms of the optical depth. So these are some of the basic definitions of what the mean free path are. And again, while doing rough calculations, we often just compute the mean free path like this to understand what is the region, what is the length of the region over which the absorption will take place. Now, I will show you the full solution of the radiative transfer equation, including both the emission as well as the absorption terms. So what we usually do is we transform this ds variable in terms of the optical depth, because as I told you, the optical depth can be written in this differential form, which is d tau nu equals to alpha nu ds. So now we sort of use this relation. So we divide, so this is my basic radiative transfer equation. We divide the left and right hand sides by alpha nu. So yes, I can see some raised hands. I'll come back to you shortly. So then once we divide by alpha nu, we can recast our radiative transfer equation in this form, which is di nu by d tau nu equals to minus alpha nu plus S nu, where S nu is a ratio of the emission coefficients to the absorption coefficient. Now, what we have done here, we now have a simple differential equation, or an ordinary differential equation, that is dependent on just the I nu, which is the main variable that you want to solve for, and this S nu, which is called the source function. So for any material, we can always find the source function, because the J nu and alpha nu are properties of those material itself. And once we find that, we can always find the evolution of the intensity as a function of the optical depth. Now, this is just a simple integral I have given here, and this notes will be uploaded, so I'm not going to the details of the mathematical derivation. But you can do this by performing an integrating factor. There's a small typo here. I have to check this. T should not be there. It should be D down here. But after changing this using the integrating factors, you end up with a solution that looks something like this. You firstly have this part of the solution, where you have your incoming I nu at a tau 1. Tau 1 is the starting point of your integral path. So if you're performing the integral over a path length of starting from S1 to S2, S is this path length. If I go back to the figure, let's say. So if suppose this is the starting point S1 and this is the end point S2, and we want to find the change in intensity over this point. So then we can also define the optical depth at S1. For example, if S1 is a starting point with no absorption, it will be optical depth of 0. So tau 1 would be 0. But essentially, the solution looks like this, where the first part is just like an absorption term that you just had. And then you have the integral over the source function. Now, look at the source function. Source function is J nu by alpha nu. Now, suppose there is no emission that is being added to the system. So source function is 0. So this part is 0, and you get back the trivial solution of just pure absorption. Now, in most of the system, that is not the case. You have an added source function, and then you can devise a solution and look at it in this way. So this is the formal solution of the radiative transfer equation. It looks simple now, but then as you add more and more physical processes, performing this integral becomes very complicated and very challenging. And defining the source function as a function of the optical depth is also very challenging. So then what we have to usually do is rewrite the source function under several approximations, say Taylor expansions, and then perform this radiative integral. There are several immediate regions of study where this is applied. And one of the most important fundamental regions or topics is when you want to find out the radiation on the upper regions of the stellar surface. So you're learning about stellar structures, and you would know that the radiation due to fusion and everything coming from the center of the star will have to pass through this dense region and come out from the top and then escape out. And it is in these regions we have to solve for this source function. And the source functions gets complicated because you have emission from different layers. And each of these layers can be a pure black body, or you can have added chemical reactions that take place, which can add to the emission. So that, and that's why the source function needs to be updated as you move along. And this take quite involved calculation. But the basic formal solution looks like this. In the last 5 to 10 minutes, I will just briefly introduce the concept of blackbody thermodynamics, and then I will end for the day. So since most of you have done bachelor's and master's, some are from the BTech background, but most of you from the general physics background would have learned about blackbody radiation and basics of thermodynamics. So this is sort of a recap. The reason why I'm saying this is because these concepts would be used later on in the subsequent slides. So what is the definition of a black body? So a black body is a system where the radiation is in equilibrium with the system which is not changing itself. So if a system is steady and has a temperature T, and the radiation itself is interacting, so the photons are coming and interacting with the system. And as you know, as a photon comes and interacts with the system, the photon's frequency can change. But after a lot of interactions, the photon entire thermal region, the thermal bath, comes in equilibrium with the radiation. Now, this radiation that is in equilibrium with a black body itself, or with this thermal system, is called blackbody radiation. So, and the intensity of that blackbody radiation, I nu, in that case, is written as B nu T. And B nu is purely described by the temperature of the system. It completely removes any other memory of any other physical processes. Now, suppose an object is in equilibrium with a blackbody radiation itself. So suppose there is a blackbody radiation that is being emitted by a system, and now we introduce another system, and these two systems are also in equilibrium with each other. Then the source function of that system will be the blackbody radiation itself. Why? Because d I nu d tau is 0. Because as the ray is passing through the system, passing through a region and encounters this body, it will not, nothing is added to the ray. So the ray encounters this body, and as it leaves the system, it emerges as a blackbody radiation itself, because entire region is immersed in this radiation field, which is a blackbody radiation field, and everything is in equilibrium. So amount of emission and amount of absorption is same in some sense. So if I just go back to my previous slide, d I nu d tau is 0, which means S nu for the system. And remember, the source function is a property of the system itself, J nu and alpha nu. So source function is just a blackbody radiation. So the blackbody radiation, so if you immerse a thermal system in a blackbody radiation and everything comes in equilibrium, then the source function is just the blackbody radiation itself. And this comes from the basic definition of this property. And just from this, the fact that source function is blackbody radiation, we get a very fundamental law, which is called the Kirchhoff's law, which says that the emission coefficient and the absorption coefficient are related by the blackbody radiation. So if you have a system that can be made into become in equilibrium with the blackbody radiation, then Kirchhoff's law applies. So if you know the emission coefficient of the system, you can immediately find out what the absorption coefficient is, because they are related by the blackbody radiation. And what this law tells you is the fact that the amount of radiation that is absorbed is compensated by the emission by the system, so that the total emission or the total change in the intensity is just the blackbody radiation. There's no total change, and the intensity remains a blackbody radiation. And for such a system that is in thermal equilibrium, we can find that the energy and energy density is related to the temperature of the system, as Ut equals to some constant to the fourth power of the temperature. I have given a derivation here. This is just for notes. I'm not going to, of course, talk about the derivation in this lecture. But when I upload the notes, you can look at the derivation here. So these are some of the properties of blackbody radiation that you need to be aware of. And this fact that the energy density is related to the temperature, fourth power of temperature, that is also called the Stefan's law. And the Stefan's law is the luminosity or the flux that is being emitted by a thermal system is sigma times T to the power 4. And let us see how that comes about. So suppose you have a blackbody radiation field, I nu, which is the B nu now. Then the total energy density of the radiation is related to the intensity as 4 pi by C B nu. And this is not something that I'm picking out of my head. This is something that I had discussed last lecture. Yes. So when I talked about the energy density in a radiation field and how that is related to the intensity, I had showed you this. So as you can see, the energy density is related to this intensity in this way. And if you just integrate over the frequency, you get the total energy. And this is what we are doing. We are relating this this fact, which is U nu is I nu by C d omega integrated over the entire frequency, which is 4 pi by C J nu. So U nu is 4 pi by C J nu integrated over the solid angle. And this is what exactly we are writing here as well. U nu is 4 pi by C J nu. J nu is the same as the blackbody radiation. Okay. which is the B nu T function. So blackbody radiation is given by the Planck function. I'll come to that later. So then if you integrate over the Planck function over the with the frequency of using the Planck function, you end up with something like this. And this Planck in the frequency integrated Planck function will give you the is related to the fourth power in temperature. And as I had again mentioned to you last time, the flux coming out of a spherically isotropic system, isotropic radiation, let's say a spherical region with isotropic radiation, the flux is related to the intensity as F equals to pi b. Again, this is was taught in the previous lecture. So the total luminosity is just F is the sigma times 10 to the power 4. Luminosity meaning what is the flux being emanated from the surface of a system. And this is what Stefan's law is. So for Stefan's law, the Stefan's constant sigma, that you can relate to the more fundamental constant that comes from the blackbody, the definition of the blackbody radiation density. So this is called the radiation constant A, which is 4 sigma by C. This pi goes away because the intensity is related to the flux in this way. So these are just some definitions just to let you know what is the property of a blackbody radiation field. And okay, maybe I'll just introduce the last 2 slides and then, okay, last 3 slides and then stop. So I have been talking about the blackbody radiation. I will not give you the derivation of the Planck function because it involves statistical mechanics, which is beyond the scope of these few lectures. But you should know that the energy density term here is energy density. So this is energy density integrated over the solid angle. This can be expressed in this way, which is the energy density of a radiation field that is in thermal equilibrium with the blackbody, which is a blackbody radiation field, can be written as 2 nu square by C cube h nu by exponential h nu by kT minus 1. And then we know that the energy density of a radiation field is related to its intensity in this way. And again, this is something that I had discussed in the last lecture. So for the blackbody radiation field, the intensity of the blackbody radiation field is just this. And this is called the Planck function. And there are 2 limits of this. One is the small frequency limit or the large wavelength limit, where h nu by kT is much less than 1. And you can expand this, this coefficient in the exponential, and the 1 cancels off. So you have 2 nu square by c square kBt, because you have h nu by kT that comes out. And then, so these are the large wavelength or small frequency regime. And this form of the Planck function is quite often used to describe the radiation, for example, in radio astronomy. Because as you remember, in radio astronomy, we deal with large wavelengths to the order of meters. And so this becomes relevant, but because typically the temperatures of the system that we are considering are such that h nu by kT is less than 1 for the frequencies of radio astronomy. Whereas in the other limit, the Wayne limit, you have h nu by kT much larger than 1, where you're considering emission at frequencies at highly energetic frequencies, much larger compared to the energy of the body in terms of the thermal energy of the body. So in that case, the Planck function looks something like this, where you can see that it's a rising phase and then a sharp decay after the exponential function, after the frequency crosses the kT. So these are the 2 limits, which is called the Rayleigh-Jeans limit and the Wayne limit, and the Planck function looks something like this. So in the earlier parts, for lower frequencies, you have the Rayleigh-Jeans limit operating, but as it reaches this, there's a turnover, you can see, and it's almost following a new square dependence. So if you look at these 2 functions, both have a new square dependence, so a power law of 2. So if you plot a log-log plot, you will have the exponents varying as a straight line with a slope of 2. And then as it reaches regions where h nu is close to kT, the exponential term kicks in over here. And then you have a sharp exponential decay. So this is how a blackbody exponential looks like. And you can see that the peak emission is always can be found out by just taking a differential of this, and this is related to the frequency as h nu max is 2.82 kT, and this is a widely used property to understand what is the typical frequency for a body at a given temperature, and this is called the Wayne's law. And just to give an example, one of the most well-known black bodies is the spectrum that is actually observed and very finely measured by us on Earth is the cosmic microwave background, the CMB. And so this is an actual example of a black body that we see all around. And black bodies or black body emission is often used as an approximation for describing many astrophysical sources which have a finite thermal temperature. So I will end my lecture here. We have time for a few questions. So let's see. I saw some hands up. Several hands up. I'll take a few questions now. So first is Vikrant.
Good morning, sir.
Good morning.
Sir, actually, we have discussed about the absorption cross-section, which is basically related to the probability of the absorption of the photon in the medium when it is passing through.
Right.
So, sir, it is also possible that the absorption cross-section is changing itself.
Yes.
Due to the interactions with the particles themselves.
Yes.
So the equations, especially the differential equations we have discussed, do they include this kind of phenomena too?
So let me first state that the absorption coefficient for a single particle remains fixed, right? Because that is given by purely quantum mechanical transitions. However, as the particles, as you rightly said, interact and change in composition, then the absorption coefficient can change. So just for a single part, a single element. So as we'll talk about tomorrow, the absorption coefficients are actually related to the transitions between different levels. And the transitions between different, so going from the quantum mechanical description will depend on the probability of for how long an electron can stay in a heightened state and then come down, etc. So those are related to the time scales of the quantum mechanical transitions. But you are right that the absorption coefficient can change. For example, if the composition of the region is changing, so you have more particles. So particles with different compositions will have different absorption coefficients. But suppose in a region, you have a flow of a different material that is changing the composition. So the net absorption coefficient can change. And all those things will have to be treated in a dynamical way. And that is something that that is difficult to do, but in actual simulations, they are incorporated when you do time-dependent evolution of intensity and absorption in a system.
Thank you, sir.
Thank you, Vikrant. So next is Nitin.
Hello. Good morning, sir.
Good morning, Nitin.
Sir, on slide 13.
Slide 13. Yes.
Sir, what is the range for the any medium to be in a thin regime?
What is the range? No, so there is
for tau nu.
Are you asking what is the range of tau nu?
Yeah.
So tau nu, as you can see, completely depends on the integral here. So it depends on the extent of the material. If the region is quite thin, and if the absorption coefficient is not large, then it just depends on the path length. It also depends. So for example, if you have a plain sheet of material and the light is crossing perpendicular to it, and if the sheet is thin, then it has a small path length. However, if the light is falling at an angle, then if say suppose for grazing incidence, small angle incidence, then it will pass through this material for a much longer path length or a much longer time. So the absorption coefficient or the optical depth is really dependent on the direction. And its range can vary from much less than 1 to much large. So it just depends on this integral.
Okay. Thank you, sir.
Okay. Next is Sandesh.
Good morning, sir.
Good morning.
So my question is actually, as we are using the limits of S and S0, and as we discussed that we are on the receiving end of the radiations. it's a little bit difficult for me to understand how do we know what is the I mu at S naught. Because
so this will depend on the physical process. So go on.
Sir, as we discussed yesterday, that we cannot duplicate whatever things are going on in the space in the laboratories, right? So how do we know that what intensity is going to be on the other side of the medium?
So this takes a bit of trial and error. So first of all, in astronomy or in any physics, we do not really know what is actually going on so far away from us. What we do is we propose a model, and we propose a luminosity for the model or some parameters for the model. Now we assume some intensity for, say, the emission from the star, and then we propagate that intensity, that is, and let it pass through this region, and then come towards you, and then see whether the flux that you calculate is actually matching the flux that you receive. So the I nu S naught is a part of the model itself. We don't know a priori what it is. Okay. Junik, let's see if your audio works.
So I'm audible.
Yes, go on. Let me try to understand, see if I can hear you.
Okay. So my question is, when we are talking of a distant galaxy, there are a lot of sources which is emitting radiations. For example, the central black hole or the intervening stars. Now, the entire amount of radiation, when it passes through a intervening medium, such as the interstellar gas or else, all the amount of radiations are getting absorbed and then it is getting emitted. So when we are observing it, how can we classify between which one is done by the black hole or which one is done by the stars or else?
So the nature of emission for these different physical objects will depend on the properties of the systems, and so they will affect the emission at different frequencies or wavelengths. Now this again goes to so you can have mixing, but then that is not always the case. For example, let's say if you're talking about black hole systems, then we know that they are usually a high energy phenomena. So they will affect your radiation that is coming towards you, but at a different frequency range. For example, if you are just looking at the black hole, and you can also have emission from the stars in the galaxy. So stars in the galaxy will affect, for example, the radiation in the optical domain. Whereas a black hole may also contribute to the optical domain, but since it's a high energy phenomena, its spectrum would be shifted to the higher frequencies. So in this way, different objects will affect at different frequencies, and then that's why we can sort of decouple the systems in most of the cases.
Okay, thank you, sir. Sir, am I allowed to have a second question?
Okay, Junik, go on.
Sir, the optical depth part that you just explained, does the optical depth remain same for all sort of radiations, or does the thickness or thinness differs between
optical depth is just a property of the material. It has nothing to do with the radiation.
Okay, sir. Okay, thanks.
Next is Harsh.
Hello, good morning, sir.
Good morning.
So is source function always explicitly dependent on optical depth for a practical system, or if it is independent of optical depth, then what kind of system it will describe?
Source function is not dependent on optical depth. Source function is a property of just the material itself. So as you can see here, from the definition of source function, it is the ratio of the emission coefficient and the absorption coefficient. There is no need to know anything about any incoming radiation or the optical depth or the path length over which you are actually computing the source function. The source function is, it's a ratio, so it's not per unit volume anymore, but it is a property of just the system itself. Okay.
Okay, thank you, sir.
Okay. Next is Manish. So those who have finished their questions, please lower your hands. Manish? Manish, we are not able to hear you. Your audio is not very clear, Manish. Manish, I'll come back to you later. Elangbam?
Yes, sir.
Yes, I hope I pronounced your name right. My apologies if I did not. Please go on with the question.
Sir, am I audible, sir?
Not very clearly. I have to take my ear very close to my speaker. Yes?
Okay. Is it audible, sir? No.
It's not very audible, but let me try to hear the question. Go on.
Okay, sir. Sir, my question is that we consider about these derivations of things about taking the atmosphere to be isotropic. So
yes. Okay.
What is the if we take that the universe is is there any relation like homogeneity and isotropy? Like in a large scale means like if there is isotropy and homogeneous, then
so let me try to summarize the question because maybe it was not very clear to many. So what you are talking about is our assumption of isotropy and how valid that is.
Yeah.
Now the thing is, we are talking about emission. We are not talking about some grand scale emission like this. So you're talking about whether the universe has isotropy and homogeneous, etc., etc.
Yeah.
We are talking about emission from a physical process driven by a system. Okay, and it can be sort of decoupled from the rest, what is happening in the rest of the universe. And isotropy is not always true. We have emission for many examples of non-isotropic emission. So it's not always true that emission from a given system is isotropic. What you're talking about is more relevant for large-scale phenomena. For example, the cosmic microwave background.
Yeah.
That is isotropic or not. That is an open debate right now, and people are still trying to find out sources of an isotropy, which will give you some clues about what the Big Bang was, etc., etc. But for given physical processes, it does not need to be isotropic or anisotropic. It depends totally on the nature of the process.
Okay.
Thank you, Langam. I will conduct these things for maybe 3 more minutes till 11:10 and then move off. So next is Anik.
Yes, sir. Good morning, sir.
Yes.
Sir, I am asking whether all these equations they are including the relativistic effect, or they are just
no. These are they do not include the relativistic effects. Okay.
But sir, this phenomena we are observing the radiations. So why we are not using those equations?
What do you mean by relativistic effects?
Sir, because we are looking at the radiation, they are definitely.
But what
electromagnetic radiation?
But what relativistic effects are you talking about?
Like sir,
where will relativity come here?
Equation.
Where do you think relativity?
Maybe, sir, because when you even if you are talking about the suppose if you have a spinning black hole, or if you have a body which is rotating fast enough, and then you're getting the radiations, so will not that affect?
So what you're talking about, the relativity comes in when you talk about how the path length is getting affected by local motions, right?
Okay.
So it has nothing to do with the emission from the source. Emission from the source will have relativistic effects. So that will be encoded in the form of the J nu or the emission function.
Okay.
And I will talk about this. So for example, synchrotron emission, for example, has strong effects of relativity because we have emission from fast moving electrons that are gyrating along magnetic fields with Lorentz factors of 100 to 1 million. Okay. So there are relativistic effects there, but they're all encoded into the final form of J nu. So just from the point of view of radiative transfer, we have ignored relativistic effects for anything that is, for example, moving media. We are not considering a media that is moving with speed of light or something like that. And for those, the radiative transfer equations, as I also responded yesterday, will change. Thank you, Anik. Maybe I'll take 2 more questions. I'll come back to Manish because he had his hand raised. Manish, let's see if we can still hear you. Manish, I think your audio is still not working. I also remember you had similar issues yesterday. Hello? So unfortunately, Manish, I'll have to move on, and you can ask your questions later in the Google form when that is ready. Thank you. Anjali?
Yes, sir. Sir, can you hear me?
Yes, I can hear you.
Sir, my question is regarding the cosmic wave background. Sir, on the y-axis, I saw that we have plotted the dipole intensity. So, Why are we considering all the particles as dipoles in the interstellar?
These are not dipole intensity, but this is the intensity measured by a dipole antenna. You would know more about this in the cosmology lecture, I think. So this is not really relevant for this. But you are absolutely right. If you want to know further about it, read the review article by George Smoot in 1997. There they will talk about how this spectrum is measured. This is measured by the satellite called COBE using a special instrument called FIRAS. And there the emission that is observed in terms of the instrumental response is what is being quoted here. This has nothing to do with the actual dipoles in outer space of the universe. Okay, last question, Astha.
Yes, sir. Am I audible?
Yes.
Yes, sir. I want to just add to the thing that when the students were talking about the optical thickness and thinness of the medium, can't we just determine it by looking at the spectra? Because for optically thin medium, the formula is I mu is equal to J mu L. So it is basically dependent upon emission, right?
That's right, yes.
Optically thin medium will have the emission like spectra, but for the optically thin medium, we have I mu is equal to source function, which is directly correlated with the Blackbody function. So for the optically thick medium, we will have a Blackbody kind of curve.
That is right, and that is exactly right. For optically thick medium, we'll have a Blackbody radiation field. So in the limit of the optically thick, if you just take the solution here, in the limit of the optically thick, I am not discussing all these things in detail over here, of course, but in the limit of the optically thick regime, or tau 2, for example, much greater than 1, your intensity approaches the Blackbody spectrum. So, for example, let's say a ray that is entering the atmosphere or entering, say, the depth of a star. In the outer layers of the star, it can be mildly optically thin. So it may have a transition from optically thin to thick. But as it is going deeper and deeper into the star, the optical depth is increasing, and then it sort of loses its memory and becomes just the Blackbody radiation.
Yes, sir. So, sir, by looking at the spectra, can we just determine the optical thickness and thinness?
No, not by looking. Looking at the spectra, you can model the spectra by assuming a functional form of the emission and the absorption coefficients and the path length. So the spectra that you observe, that is just a distribution of intensity. Just by looking at the spectra, you would not know. But suppose you know that what the spectra should be of the emitting system. Now the observed spectra, if that has a lower intensity than the expected value, because you already know, for example, let's say it's a Blackbody. So then, if the observed spectra is lower, then you might know that it has passed through a medium that was optically thick, or had some regions that was getting absorbed. If it's completely optically thick, it will be Blackbody, but it's not completely optically thick. Okay.
Okay, sir. Yes, sir.
Okay, so unfortunately, I'll have to stop here because we'll have to move to the next lecture. The lecture, the Zoom link might remain open. Santosh or Sagar, are you around?
Hello, Dipanjan. Yes, I'm here.
Yes. So can we then try to just keeping the Zoom link alive and go to the next lecture? Can we test that?
Sure.
Okay. So thank you, everyone. We will likely mute you and try prepare for the next lecture. Stay around. We are not closing the Zoom link now. So Santosh, is the YouTube working as expected?
Yes, YouTube is working as expected.
So what I mean is, were you able to stop the stream and restart it again? Can you check that?
Yeah, so I'm just stop the streaming.
Mm-hmm.
Just I'm just ending the stream.